So good morning, everyone. So I'm Olivier, coming from UC Louvain from Belgium. And it's a pleasure to be here again at SCM. So I want to thank the organizer for that. And of course, it would have been better for me if the portal testing was not yesterday, but I think I will manage it. And I also would like to thank the previous speaker, but I think he left. Because he did my introduction. Actually, I will tell you a similar story about the process parameters. So my talk here is about the appearance of defects such as roughness and porosity in aluminum silicon 10 L PBF parts when the job load is changing. And when I say job load, I mean the surface to build per layer. So at UCL, since 6 years now, we build a lot of parts with a lot of different materials. And we often end up with really strange defects on the surface, different roughness on the surface, especially with the aluminum silicon 10 alloy. So this is the case here on the heat exchanger we built with Safran on a Belgium research project. But we also observed that on a fancy student project here on a bottle opener, and also on standard tensile test samples, as you can see on the bottom here. So the idea behind that is that we have a drifting of the process window during the LPBF process because of the build-up temperature. And actually, when we are looking to the steady state equation, so the so-called Rosenthal equation, of course, we see that the melt pool size will depend on the process parameters, so the power and the scan speed, but it will also depend on the substrate temperature. And because of the build-up temperature during the process, this temperature can increase or decrease. And of course, your selected parameter can no longer ensure stable melt pool during the process if the build-up temperature is changing. So in this talk, this is what we want to study. We wanted to highlight those effects by using a simplified sample geometry. And we also wanted to estimate how badly this effect will affect the material health by quantifying the roughness and the porosity, depending on the parameters we choose. And at the end, we also wanted to correlate the experimental measurements with FA model, but this is still an ongoing project. So to study this drifting effects, we built some simplified geometry, as you can see here, some pyramidal sample. On those pyramidal samples, the surface to build is divided by 2 depending on the step. We have 4 steps, and the size of the step are 5 millimeter thick. We choose 2 thickness of samples, 3 millimeter and 1.5 millimeter, because as you saw in the previous presentation, the thickness is has also an effect. We choose a contour and a bulk strategy, and of course for those 2 parts we selected a lot of parameters to have enough data to be sure to observe effects we want. So for the bulk parts, we choose parameter around our so-called optimized parameter on our equipment, but we also choose 1 hotter and 1 colder parameters. And for the contour part, we selected our best parameters to get a really nice roughness. So the idea at the beginning of this work was that when we built such kind of a structure, for example, on the top of the structure, the laser will coming back on each layer too fast, and then the top of the structure will be too hot, so that we will have a really huge drifting effect. And to avoid that, we also decided to print a similar batch, but with an adapted time. That's to say, a fixed time per layer. So you have here the time per layer of the normal batch. And of course, the time is decreasing because the surface to build is decreasing as well. And on the other batch, the time per layer is fixed. On all our sample, we did a lot of characterization. Of course, we did roughness characterization because the first effect we saw was on the surface of the samples. But we also study the porosity, the microstructure, the male-pole shape, and also the thickness of the samples and the contour male-pole thickness, because those are the male-pole that we can easily measure after the process. So we have 48 samples. So from here, I cannot show you all the picture, all the result, because there are too much results. And I'm going to show you the most relevant one. So first thing first, the visual aspect of our samples. So you can see here for the normal batch above, the adapted one with fixed time per layer. We clearly see on all the samples that there are a lot of inhomogeneities on the surface, depending on which step we are. We can see that those samples are quite good, but still we are still able to see some stratification. And if we take a closer look to the best samples and the raw samples, we see on the left that this is actually what we want to have on each samples, on each part you want to build. You want homogeneous surface everywhere. And on the right, this is what we mostly get. We have a lot of different color here. And when I mean color, of course, I mean surface roughness. So we measure the surface roughness of all our samples. And as you can see here on the left one, the surface is quite good. This is actually what we want. And on the other samples, the roughness is going down, then up and up. This is really unstable. So this is something that we want to avoid. But in the framework of this study, this is what we wanted to get, to analyze those effects. So we took our samples, cut it in half, do some polishing, some image processing, and we end up with such kind of results. At the third glance, we just see standard LPBF porosities, but if we take a closer look at the two last samples, this is a really surprising results, because we have different kind of porosities depending on the step, while the process parameters are the same between the first steps and the last steps. So on the bottom here, you can see that we have lack of fusion porosities. On the second step, the material becomes somehow dense, less porosities. Then we end up with, on the third step, with a lot of keyholes and metallurgical porosities. And on the last step, the amount of porosities decrease again. So this is really inhomogeneous. And as I said at the beginning, the idea behind that is that we have a huge drifting of the process window, or the other way around. It's like the process parameters are moving across the process window. And then we can say that at the bottom, the condition during the printing were cold, then a bit hot, then too hot, then the condition cooled down a bit and we lose some porosities. This is what we wanted to highlight. So if we take a look at the thickness and the roughness of those samples, you have here the normal batch and here the adapted batch. And the story behind that is quite the same. So for the thickness, we see that there is an increasing of the thickness from the step 1 to the step 2 to the step 3, and then a bit decreasing of the thickness. The roughness has exactly the opposite trend, and this is the case for the normal batch and the adapted batch. We clearly see that the roughness is decreasing and then reach a minimum, and on the other samples, the roughness is decreasing and then increasing again. So if the thickness here of the contour male-pole are increasing, it means that the build-up temperature increases also. And if the thickness of those contour male-pole are decreasing, it means that the temperature of the sample is decreasing. And this is exactly, and we see exactly the same things with the roughness, but for that you need to know how roughness of this alloy works. And for aluminum silicon 10, it's easy to understand. If you put more energy on the contour, the roughness will decrease, and if you put less energy on the contour, the roughness will increase. And this is quite clear here. the thickness is increasing, meaning that we have more energy on the contour, then the roughness is decreasing. And then when the thickness is decreasing, the roughness increases because we have less energy. So we also measure the build plate temperature during this process. On the left here, so you have the temperature of the normal batch and then temperature of the adapted batch. For the normal batch, we clearly see that the temperature of the build plates is increasing during the step 1 and the step 2, reaching a maximum in the step 3 and then decreasing on the step 4. And this is exactly the same story that we see previously on the porosity and the roughness. We also did some easy FA simulation to understand that. And what we saw is that the build plate temperature and the samples temperature during the process are always the same. So of course, if it's with aluminum have a huge thermal conductivity, and the samples were not so high. So this is not so surprising, but now we know that the temperature the substrate temperature we see in the Rosenthal equation is actually our build plate temperature, which is also the build-up temperature. And then now we understand why we have such difference in the roughness, in the thickness, in the porosity of our samples. As this temperature is moving, even though the process parameters are not moving, the melt pool of our sample will also will be modified. So in this work, we used pyramidal samples to highlight the thermal issue. And we also saw that the material health is really badly affected by those effects studied here. And we also see that the defect appearance can be explained by this build-up temperature. So this is the temperature of the build plates during the process. So that's it.
Thank you for your nice presentation. From the audience, is there any question on this talk? We have time for one question. Okay, I have one question. One thing, you studied the roughness and the internal porosity. Did you manage to check if there is any variation in the residual stresses in these two cases?
Not yet, but there is a variation in the microstructure as well, because the cooling time changed between the steps. But for the internal stress, not yet, yeah.
But overall, very nice technique. It's the first time I'm seeing it. Very nice.
Thank you.
Thank you so much. Thank you.